Hello, this is John Buck back again. Tonight I'm going to show you an example of how we can use the Fourier transform properties to get to an impulse response from a difference equation. So tonight's topic is going from difference equation to an impulse response. Okay, and the example we're going to do is just to find the impulse response for the causal linear time invariant system specified by the difference equation shown there, y of n plus 1/4 y of n minus 1 minus an eighth y of n minus 2 equals 14x of n plus x of n minus 1. And there's sort of three key steps here I'm going to lay out first for you. The first step is to use Fourier transform properties to get the frequency response, which is the Fourier transform of the output divided by the Fourier transform of the input. So we're going to do that first. Once we have that, the second step in our approach is to use partial fractions to break h of e to the j omega, the frequency response, into a sum of first order terms. And then the third step scrolled the wrong way there. The third step in our approach then is once we have that sum of first order terms, is that makes it very easy to do the find the impulse response h of n using very simple first order inverse Fourier transform. Okay, so that's like the roadmap of where we're going. I wanted to lay that all out before we get started, so you can sort of keep yourself oriented in the big picture of where we're going. So the first term just comes down to basically three properties. The first step, which is to use linearity, to use well, really two properties, I guess. There's linearity, but we're going to use both superposition and scaling, and then also the time shift property here. And this is very straightforward. Let me create a new page and then put the difference equation at the top of that. So again, the equation we're looking at is y of n plus 1/4 y of n minus 1 minus an eighth y of n minus 2 equals 14x of n plus x of n minus 1. And so we take the Fourier transform term by term, because if something is true in the time domain, we take the Fourier transform of both sides, it will still be true in the frequency domain. So the first term is just y of e to the j omega. The second term, I get 1/4 from the scaling, and then the shift property says, well, this was shifted by 1, so I multiply by e to the minus j omega, the Fourier transform of the output. And the next term is minus 1/8. And in this term, the shift is 2, so my exponent becomes e to the minus j omega 2, where this 2 is because of the shift of 2, times y of e to the j omega. And this is equal to 14x of e to the j omega plus e to the minus j omega. Let me scroll over a bit here. Times x of e to the j omega. So again, I've used the shifting property several times here, where shifting in time is equivalent to multiplying by e to the minus j omega times the shift and frequency. The next step, again remembering where in my roadmap, is I want to get solve for the ratio of y of e to the j omega times x of e to the j omega. So to do that, I'm going to factor, I need to factor the y out of all the terms on the left side and the x out of all the terms on the right side. And so when I do that, on this side, I'll get y of e to the j omega. Well, the first term, when I factor that out, it's everything. So I just have 1 plus 1/4 e to the minus j omega minus 1/8 e to the minus j2 omega is equal to x of e to the j omega 14 plus e to the minus j omega. Okay, so again, this is the same as the equation I just had. I've just pulled the y and the x out because I'm getting ready to divide it to solve. Remember, what the next thing I want to find is I want to solve for h of e to the j omega is the ratio of the output over the input Fourier transform. And so to do that, I'm going to take this term here, this x term, and divide both sides by it, so it effectively goes into the denominator here. And to get y left alone, I need to take this whole fraction and divide it that way. So this is sometimes called cross-dividing. And when I'm done with that, what I'll end up with is on the left-hand side, I'll have this ratio. And the right-hand side, well, this will be the numerator. So I'll end up with 14 plus e to the minus j omega over 1 plus 1/4 e to the minus j omega minus 1/8 e to the minus j2 omega. Okay, and let me copy that y over x down here because it makes it a little easier to see how this really is the same equation. And when you first start doing these, sometimes it's easy to get them upside down, so you do want to always double check things. But you want to multiply, if I multiplied both sides by x of e to the j omega, this numerator would give me back this right-hand side right here. I can use my pointer for a second, right? If I multiply this term up, if I multiply both sides by x of e to the j omega, those two terms would give me this back. If I multiply both sides by this denominator here, this 1 plus 1/4 e to the minus j omega minus 1/8 e to the minus j2 omega. If I multiply both sides by this, it would end up here in the numerator on the left-hand side, and I'd have this back, and I'd have my original equation. So here's the first step. If I were asked to find the frequency response of the difference equation, I'd be done. I'd have it right here. This would tell me how the system responds to each frequency omega between minus pi and pi. I could plug in and figure out what the frequency response is, both the magnitude of the gain and the phase if I needed that. Unfortunately, we don't get off that easy. The example we're doing tonight is we want to get to an impulse response. I say, well, I know the impulse response, again, remembering what this thing here is the frequency response. If I could take the inverse Fourier transform of this, right, there's a Fourier transform relationship or correspondence, that would give me back h of n. Unfortunately, looking at this form right here, it's not an easy inverse Fourier transform. You can't just plug this into the integral of h of e to the j omega times e to the j omega and d omega and solve that integral straightforwardly. It's a pretty messy integral. You'd need to know some complex analysis. So what we're going to do now is be what good engineers are. We're going to be smart and lazy, using partial fractions where we add some extra algebra, but by the time we're done, we end up with inverse Fourier transform terms we can do one at a time just by looking at them by inspection. Okay, so let's create a new page to go on and do that, and then I'll bring the h of e to the j omega over with us here. So on my new page, again, we're starting from what we just got to, which is our frequency response, h of e to the j omega is equal to 14 plus e to the minus j omega. And then I have 1 plus 1/4 e to the minus j omega minus 1/8 e to the minus j2 omega. And the first step I need to do, the idea in partial fractions is I want to take this apart into the sum of first-order terms. which is equivalent to saying that originally this denominator here must have been, this stuff right here, must have been a common denominator from several terms that were first order. So to find that, the first step I need then is I need to factor this denominator. I say I've got the numerator I'm going to leave alone, but I need to factor the denominator into first order terms. And if I've not practiced at doing that, it's a good thing just to set up and say, well, based on the numerator here, I'm going to guess the first term was 1. And then I say I need to factor an eighth. I could do a couple things. I could just use the quadratic formula and find the roots. But I can also look at this and say, well, I've got two terms that are e to the minus j omega here. I need to know their coefficients. Let me guess at easy, clean factors of this and hope I get lucky that one of them works. I say, well, I can factor the integer factors of an eighth. It could be 1 and an eighth. Well, not integer. I guess these are easy rational factors. Another one would be a half and a quarter. And I'm trying to keep things in this form because we'll see in a little bit. This leads me to an inverse Fourier transform I can do just from looking at it in most books. And now I just need to figure out, well, what are the signs here? If I sort of do this one piece at a time, let me quickly clean that up a bit. Oops, making messes everywhere. Right, so I just need to work out the signs. Well, if the final term, the second order term, is minus, I need 1 to be plus and 1 to be minus. And if the middle term is positive, that means the larger term has to be the positive one. So I'm going to put a plus here and a minus there. And then I can quickly FOIL this out in my head to make sure this works, multiplying everything through. I get a 1 for the lead term. I get plus a half minus a quarter for the cross term, the middle term, which is plus a quarter, which matches here. And then I get plus or minus an eighth, e to the minus j of 2 omega. So that's great. That's the first step I need factoring. If you're not used to factoring, or if it makes you uncomfortable to do this with e to the j omega, you can do it with x's. And maybe I'll add that at the end. I'll come back and do this if you want to see that. You can fast forward. Maybe I'll show you actually two partial fraction tricks for this, and then see. But I'll put those both at the end so we can just go forward now. All right, so the next step to the partial fractions is to say, now that I have that factored, I need to write that as a sum of first order terms. And an important piece in doing that makes it easy is that both of these are first order. They don't have higher order, anything, no squared terms in the denominator, which you can still do, but the algebra gets more painful. And so I say, well, what I'm betting on is that I can write this thing here is the combined least common denominator form of the sum of two fractions that look like this. And the reason I want to get here is this is an easy inverse Fourier transform. If I had just something that looks like this term, or just something that looks like this term, I could break them down very quickly to the time domain. So if I can put it in this form, it's going to take a little work, but it's going to be the payoff that the inverse Fourier transform is very straightforward. So the question is, I need to figure out what A and B were. And now I sort of look at this and look back at what's going on up here and say, well, if I multiply these two together to make a common denominator, my numerator would have been A times this denominator plus B times that denominator. Right? So what I have in the numerator would be, I know that 14 plus e to the minus j omega. Oh, and I'm going to back this up one thing. I'm getting set up to do one thing. I am going to start writing the terms in different colors. I'm going to put all the e to the j omega terms in green because it's going to sort of highlight the way we get the answer here. So if I multiply these two together, I'd have a term that was A, and then I'd have minus A times 1/4 times e to the minus j omega. Right? That's this denominator times this numerator. And then I'd go back the other way, and I'd have plus B times another plus B times a half e to the minus j2 omega. So I'd have this times this. So adding all that together is how I got this numerator for the right values of a and b. And the reason for the colors here is to show that although this looks like one equation, it's really two equations hiding inside. Because for this equation to be true, all the constant terms have to work out, and all the e to the j omega terms have to work out. Okay, so it looks like one equation, but it's really two, because I'm matching things term by term here. And so when I do that, let me pull this apart now. I'm going to basically take all the white pieces into one equation and all the green pieces into another, because for these equations to always be true for every omega, the green pieces have to satisfy one equation and the white have to satisfy the other. Now, obviously, you don't have to do this with two colors when you're doing it on your own, but I'm using a little color here to try to really emphasize for you how I'm breaking this apart to get these two equations, because the first time people do this, first couple times, they can sometimes find this confusing. So again, for the constant term, what I end up with here is 14 is equal to a plus b. Right? So I'm just going across saying the constant terms in this equation give me this equation. The second term is the e to the minus j omega term, the first order term. And what I would get from that is the coefficients. I take the coefficients out. So this is 1 times e to the minus j omega has to be equal to minus 1/4 a plus 1/2 b. Right? Those are just taking all the coefficients of e to the minus j omega, so those terms all line up. Now I have two equations and two unknowns, and I should be a happy camper at this point. So if I want to solve for this, two equations and two unknowns, I'll do it by hand. 3 by 3 I'll usually do by hand. If it gets much bigger than that, I've had questions about that. Usually at that point I go get MATLAB or something else, a computer, to solve a 4 by 4 system of equations. So I usually don't go beyond this for 2 by 2 or maybe 3 by 3 in this case. So if I want to solve this, I'd say, let's see, the next thing I do is I would multiply this whole equation by 4. And when I do that, I'd say this equation is also equal to 4 equals minus a plus 2b. Or equivalently, I could move the a and the b around. That would give me a is equal to, if I bring a over here, I get 2b minus 4. And I keep scrolling up my page here. I'm now going to take this equation here. I'm going to take this solution for a and plug it in back up here to get a solution to that equation. And when I do that, coming back over here, I'll have 14 is equal to 2b minus 4, so that's what I plugged in for a, plus another b. So combining those terms, I get, if I bring the b's together and I move the 4 to the other side, I get 18 is equal to 3b. And so b is equal to 6. And if I solve here, well, a plus b equals 14, that tells me a equals 8. So now these equations here, these values here go back in to the stuff that's just off the screen. This tells me what the numerator of each of these terms are. So it's going to be 8 over 1 plus a half e to the minus j omega plus 6 over this term here. So let's start that on a clean page. All right, so after working through the partial fractions, what I've found is I've got h is equal to, I've got 8 over 1 plus 1/2 e to the minus j omega plus 6 over 1 minus 1/4 e to the minus j omega. So again, I just got that by going back to the previous page and putting a and b in up here for these equations. I got to this. And now this is a Fourier transform we should recognize. These both came out of the infinite geometric series, so they are geometric sequences, something that goes like a to the n, where right this is using, again, you can find it in your table or whatever is comfortable for you. But we've seen the example, and there's actually an earlier video on this too if you want to look at it, that if I have a to the n u of n I end up with the Fourier transform. This corresponds to the Fourier transform of 1 over 1 minus ae to the minus j omega. Okay, so in this left one, my a would be minus a half, because I have minus a down here, so I need to get plus a half. A would be minus a half. And then scaling by 8, I just use the linearity. So if I use that transform pair, I can very quickly say the impulse response here, h of n, is going to be 8 times minus a half to the n u of n. And just to annotate that, make it a little clearer, this is what I got when I said a equal to minus a half. I make this term match that one. Well, a equals minus a half and then multiply by 8. So I get this term here. And the second term says I get plus 6 times, and in this case a would be a quarter. So I get a quarter to the n u of n. So again, in this case, a was a quarter for this term. So I have two geometric terms like this, and it all works out. I forgot to mention something I would normally recommend you do also, which is at this point, when you get your partial fraction expansion, I would multiply it back through to double check your answer. So I say, maybe I'll do that sort of in blue on the side here in parentheses, which is to say if I multiply this through, that parentheses is going to be misleading. Let me take that away. So you don't necessarily have to do this, but to double check, I would say I get 8 minus 2e to the minus j omega, and then I get plus 6 plus 3e to the minus j omega, all over a common denominator, which is what I should get. That part's pretty easy. And when I simplify that numerator, I get plus 14 plus e to the minus j omega. So this all gives me back what I wanted. I've been doing these for a long time. I still find ways to make silly algebra mistakes. So I always check my answers like this. So I wanted to model that behavior for you too. Okay, so again, to recap, we've gone from the difference equation to the impulse response, and we've done that with this three-step procedure. I first used Fourier properties to get from the difference equation to the frequency response, which was this step here, right? Here's my, and I say the next step is I need to get an inverse Fourier transform to get back to h of n, and the sort of mathematical technique I use to do that is called partial fractions. I guess I should have put that name up here somewhere. So this idea of taking this product of first order terms in the denominator apart, this technique gets used is called partial fractions. To break it into these terms, and the goal or the payoff in doing that is if I do the algebra, solving things term by term to get that sum form, which I did here. I got the a's and b's here, and then going on to the next page, right, I wrote it out as this sum. These turn into very easy inverse Fourier transforms using this Fourier transform pair. So that's the sort of overall point of view. I think this video is long enough, so what I'm going to do, I'm going to end this video, and I'm going to do a very short video showing two other ways to get the Fourier transform. To get the partial fractions. One that's a little more basic if you're intimidated by partial fractions and treating e to the minus j omega as a variable. I'll show you how we can just turn that into an x, and it's all the same algebra. And then I'll show you a quick trick for finding them as long as you have first order ones. So one will sort of break it down even more, one will up the ante. But I'll put that in a separate video on sort of different approaches to partial fractions. Okay, so I hope you find that helpful, and I will talk to you again soon.